Okay, I'm streaming. Or am I? All right. It says I'm streaming. Someone has to tell me if it's happening. No, someone, they can do that. The viewers. Oh, good. It's live. Yay. All right. Well, we did this a couple of weeks ago, and I had a lot of fun, so I thought we would do it again. And all we're going to do is we're just going to hang out and hang out, talk about space, see what's happening. And while I'm at it, I thought what I would do is I'm going to try to kind of make it a little fancier. So I will actually try to break up this live stream with some like full screen graphics and show the questions. I'll try and be a little more disciplined about so that people can see what question I'm answering it as we go. So I think that's the plan. And then I'll put that, hold on, I'll put that, let me do this. Apologies, I'm going to have to still get good at this. Here we go. Oops. All right. So let's see. So what I'll do is while I'm answering the question, for example, like what is the Hubble Space Telescope? I'll put that there. Yeah, it is. Right. So before we get into this, I will disappear that for now, and we'll just chat. Right. So I wanted to maybe do this on a semi-regular basis. And as always, the best way to do anything is to do the smallest possible version of it, see if you can make it go and not break. Yeah, where's the forest background? And then from there, make it better and better and better. And so I want to sort of push my live stream chops to the very limit. And so what I thought I would do is I will hang on here and try to produce a show in real time all by myself. The thing that's going to suck is that I'm going to be sort of Googling up images and typing in questions to try and sort of make it. So there may be, I'm going to take like a small delay, I think, each time that I tackle each question. But then as we move through it, we'll go from there. So that is the plan, I think. And so it'll kind of look like a question show, but it'll be done in real time and live with the people who are here and hanging out. And then hopefully, but then the people who are watching this after the fact will see it, and they can even kind of scrub through the video and see what the topic is, what we're talking about live. But I have to remember to do it in the moment, or else it's just gonna suck. So that's the plan right now. Yes, I'm gonna be multitasking, and I'm gonna try to work on a couple of my vocal tics. So I tend to go which my wife notices. She's like, you're saying a lot as you wait, and that's sort of like the sound that I make as I am preparing to get to the next question, and I really got to stop doing that. So you are my practice. So the first thing, and then I think where's the forest background, right? I'm doing this inside the house. I'm not gonna take this to the forest yet. Who knows? I might actually do this in the forest as well. So the first thing, and this is for anyone who's never done one of our live streams before, one of our the things we do, one of the rituals that we do is that people say hi to me in the chat. So if you're watching this anywhere on YouTube right now, go ahead and say hi to me in the YouTube live chat, and that's the one that I'm just bringing down here at the bottom in the show. So go ahead and put and say hi to me, and then in a second I will say hi to a bunch of you. So if you want me to say your name, that's all you got to do. And I'll give you, because this is your first time, I will sort of let you people know. Apologies to sort of a lot of the regular show watchers. We normally do the live shows at noon Pacific on Fridays. And so, but that's rough for a lot of people who, like, have jobs and live in other parts of the world. So we're gonna do this at 5 o'clock, which is good for me because that's 5 o'clock Pacific time. It's good for the folks on the East Coast. I'm sorry for the European people, but you guys get you get the best show because we do it at noon Pacific, which is like just evening for you. So a lot of our fans are European for a lot of the live shows, but the folks on the West Coast and this is good for Australians. So that's why so I'm going to try and push this to a different topic. And anyway, so once I get through this, then I think I'm going to try and bring in a guest. It would be really fun to just have an expert guest and just hang with me, and whether we actually talk about the topic at hand or whether we just hang out and drink beer. Tonight I've got a tasty stout from our local brewery, so that's gonna be keeping me going while we go. All right, cool. So there you go. You all said hello. So now I'm gonna say hi to you. So hello to Andrew McKinney, REAJ, Ben Ofa, Birdshot 1902, Brant Hunter, Brian Stab, BTT, Damien Reloaded, D-Lady14, Eric Charlin, Fleming Thunberg, Gas Dive, High Champ 1, Elcan 1, Ivo Soares, Jamie S, James Haney, Jesse Kokowicz, Jose Ruiz, Joseph X, K Wakey, Conrad Dax, Kurt Reber, Marine Iguana, that's awesome, Mitch Crane, Mitchell Peterson, Paranormal Cactus, Paul Taylor, Festerful, Preston Thompson, Raylene Keys, Raza Siddiqui, Roll Sporin, Ryan M, Sergio Patero, Sev Dust Bunny, Shane Sanders, Skunk City Tim, Titus Veridius, Tom Robin, Tom Walker, Upcycle Electronics, Wickus Vanderweer, and Eunice Sofrey. So some names there that I recognize, but a lot of names there that I recognize from doing the comments. So I think that's really cool that a lot of the people who've never had a chance to hang out live before, this is sort of a first chance to do it. So I think that's really cool. Right on. All right. Okay, so let's go ahead. My voice isn't matched with the sound. So Birdshot 1902, that can be all kinds of reasons. Mostly it's somewhere in the internets between you and me. So there's no control over that. I'm pumping out 3 megabits per second. I don't see any frames dropping, so at 30 frames a second, so it should be good. I wonder if I can do 60 frames a second. That'd be interesting. Okay, so let me see if I can do this without driving you crazy, but without people having to hear the text. So let me see if I can pull this off. Okay, give me 1 second. So I'm going to answer, what is my favorite science fiction show? So let me just mute this. You don't have to hear my typing. All right, so we're going to answer, what is my favorite sci-fi show? And, oh, that should be on. Okay, there we go. So this question comes from, oh, we lost it here. No, wait. There you go, from Mitchell Peterson. What is my favorite show? Okay. Sorry, I've still got to get better at this. Favorite sci-fi shows. Right now, obviously, I am loving The Expanse. And I was just on a podcast called Decipher Sci-Fi, and we talked for like an hour to talk about to The Expanse and sort of what I loved about it, what I didn't like about it. But just like in general, I think The Expanse is the greatest science fiction show that's been put on television in the last, I'm going to say, decade. The story is compelling, the characters are amazing, and the way they handle the sort of the exploration of space is spot on most of the time. And there's a couple of things with The Expanse that they kind of sort of go off the rails a little bit. And that, of course, is this concept of the Epstein drive. I don't want to spoil too much, but they've got this super fancy fusion drive that can go faster and faster and faster. And we just have no way to do this. And so from that, I sort of feel like every science fiction show that I watch gets sort of a freebie, and The Expanse's freebie is this crazy space drive. Because everything else, they deal with sort of the acceleration of the astronauts or the pilot and the crew as they're moving. They deal with how they deal with weightlessness and things like that. So I would say right now, The Expanse, if you haven't watched The Expanse, and they just finished season 2, and both seasons are absolutely terrific, very tight. It's great to see a science fiction story turned into television. So I love it. Now, I saw someone in the comments talking about The Colony. Season 1 of The Colony was pretty boring, really. And you said put me to sleep. Totally put me to sleep. Put us to sleep too. Season 2 is pretty good. They really, I think, tightened it up and made season 2 a lot better. So if you kind of watched The Colony and got a little bored of it, I would say give it another crack and watch season 2. Shane Sanders is saying Rick and Morty. Absolutely. Oh my God. So Rick and Morty isn't really realistic, right? Although, I mean, there's some concepts that are thought of in, about alternate dimensions and aliens and things like that. But man, Rick and Morty is so good and so funny. And so, like, if I had to pick, man, Carla, what would you do? Rick and Morty or The Colony or The Expanse? Rick and Morty. If I had to choose, I'd pick Rick and Morty. It's so good. How could I ever make that choice? I know. How come you ever make that choice? So that would be my recommendation is Rick and Morty. Now, there's a bunch of other stuff too, like Farscape. People are mentioning Farscape, Atlantis, Stargate. I love all those. The hilarious thing is where I come from, right? Western Canada. Most science fiction shows are shot here. And so all I see is home when I see them walking around in some distant forest alien planet. I'm like, no, that's just outside Vancouver. So that is that's kind of my feeling about it. Farscape is great. Lars, a bunch of people are saying that the old show of Star Trek is the best, and yeah, the wife is putting the thumbs up. All right, I'm gonna answer about longer videos. All right, so let me try this again here. Save the typing. Forest alien planet. I'm like. So many things to remember all at the same time. All right, we're going to talk about this question that came from... Oops. Here you go. Area JY. Do you plan on making longer videos in the future, or are you comfortable in the 5 to 15 minute zone? Right now, we do videos, as you said, in the sort of 5 to 10 minute zone. If you go right back to the beginning of the Guide to Space, the videos were about 3-4 minutes long, and more recently, they are in the sort of 10 plus minute range. 10 to 15 minute range. They're harder. They've been kind of dropping back down again, sort of into the 8 to 10 minute range. Now, there's a couple of reasons for that. One is I feel like I've got more to say. Like we've done 300-ish episodes of the Guide to Space, and just my writing method has just gotten more. I'm just moving to a new place, right, in the way that I write. And part of it is that my co-writer, Jason Harmer, he hasn't been working with me for about 150 episodes now. So he worked with me on the first, say, 150 episodes, and he's much more the comedian. So a lot of the earlier episodes were a lot funnier. And a lot weirder. I mean, Jason's sense of humor is, whew, and so they're these obscure science fiction references and things like that. And I don't necessarily have the same uh, sort of lexicon of references that he does, and the same sort of crazy sense of humor. I really enjoy his sense of humor, and I loved his words coming out of my mouth. But for the last sort of 150 episodes or so, it's been my writing more than my writing, and then he edited my writing to make it sillier. So that's sort of, if you sense a tonal change, that's what's going on in the episode. The sort of longer I would love to do longer episodes, but because you look at things like traditional television, Cosmos, things like that. So that is how long television shows used to be, 45 minutes. And I actually took a script of Cosmos and pulled out all the words and tried to figure out how many. It's about 4,000 words is an episode of Cosmos, the new Neil deGrasse Tyson reboot. So when I think about, and my scripts are about 1,500 words, so I would need to sort of double plus to fit a 45-minute time, with it being a more slower pace. And this is just like, this is an evolution. We don't have the budget of a Fox, however many millions of dollars per episode Fox paid to have Cosmos made, or even documentaries on the BBC and stuff. We have to evolve our way towards telling the kinds of stories that we want to tell. And they might be longer, they might be shorter. And at the same time, that there is the interaction between me and the fans, and the people who are watching what we're doing, that never existed in traditional media. And so it is a thing that you kind of bring into this process as well, like with the question show and so on. So I think that we would absolutely love to bring more traditional filmmaking techniques into what we do. And I hope you've seen better lighting in what we've been doing recently. We've got a better camera now. We're trying to focus on making sure the sound is good. Chad's been bringing in more audio. We've been kind of going to full screen images and animations and stuff more often, kind of Ken Burnsing what we're doing. And over time, I think we want to make them just longer and longer. So I think that is the sort of way that we're going to try and go. So I think there's longer stories that I have to tell, and there's shorter stories I have to tell, and you're going to get the chance to see them all. All right, I'm going to take your question, Suhendra. Give me 1 second here. All right, hold on. Let's see if we can do this right. Mute me. All right. So Suhendra Kabhametu asks, wait, you just moved your question. It was yours, wasn't it? All right. Jose, actually. Sorry, Jose Ruiz. Is your question. My question, purely hypothetical. What if the supermassive black hole in the middle of our galaxy suddenly disappeared, like out of thin air, or space, or whatever? So, this idea of the supermassive black hole, we know there's a supermassive black hole at the heart of the Milky Way. It has 4.1 million times the mass of the sun. And I think you kind of imagine this black hole as like the anchor to the entire galaxy, but it really isn't. The thing that holds the galaxy together is the sort of total amount of mass that is in the galaxy and surrounds the galaxy. And actually, it's the dark matter halo that surrounds the galaxy that holds the galaxy together and allows it to maintain its spiral shape and as it's rotating and not fly apart. It's that halo of dark matter. When you add up the total mass of the Milky Way, I forget what the amount it is. We know that there are 200 billion masses of the sun, and then we look at, say, the mass of the of that Milky Way, it's only 4.1 million times the mass of the sun. So it is a tiny fraction of the total mass, and those stars are not just the amount of mass of the universe, of the galaxy. You've got all of the planets and gas and dust and all of that kind of stuff. So it's much, much more. So really, these supermassive black holes, they're just the place in the middle where all that stuff collected, but they don't act like the galaxy doesn't need them. So you can have, and you can have these galactic collisions where two galaxies come together and they smash into each other, and one galaxy gets its supermassive black hole ejected, and that would be, there you go. So I think, we actually did do an episode of this. I think this is where we called the supermassive black hole at the heart of the Milky Way, and we called it Kevin, and we talked a bit about sort of how much of the universe is black holes, and it's not very much. All right, so let's do this question next. Roll Sporin asks, if the universe stopped expanding, would there still be gravity? You're seeing me find sort of bad pictures. All right, let's go with this one. I'm like, I don't like that picture. Okay, so here we go. Whoa. Interesting. All right, so things I'm learning here. Would there, if the universe stopped expanding, would there still be gravity? And all right, let's do it. So as we know, the universe is expanding, and this is sort of this leftover momentum from the Big Bang that happened 13.8 billion years ago, and now the universe is expanding and expanding and expanding. And so the question is, does that expansion have anything to do with gravity? And up until really the last couple of decades, it was still an unsolved question on whether the universe was going to keep on expanding, and then it would sort of slow to a halt, and then it would collapse in on itself, or whether it would just keep on expanding forever, and maybe at time infinity it would coast to a halt, or the other possibility is it would keep on expanding forever. And this was an unsolved question, and the way to get to the bottom of this question is astronomers searched for essentially the curvature of the universe. And we just did an episode on this, so I don't want to go over the whole thing again. But the measurement that they made so far with the greatest accuracy is this idea that the universe is flat. And what the implication is that the universe is going to would coast to a halt. And so it wouldn't collapse in on itself, and it wouldn't sort of keep expanding forever, but it would coast to a halt and kind of stop at time equals infinity, which will never happen. But then in 1998, astronomers discovered dark energy, and that meant that actually the expansion of the universe is accelerating. And so that is no longer really a concern, because we know that whether any kind of curvature, it's accelerating faster and faster and faster. So the question, I guess, is what does that have to do with gravity, right? At the local level, like on a planet or say a black hole, it's always going to have gravity. Whether the universe is expanding, whether the universe is contracting, whether the universe is stopped, a black hole is still going to have gravity at a local level. And same thing for a for a galaxy cluster that is held together by gravity. And one of the things that's sort of confusing is that why can you have things like Andromeda and stuff moving towards the Milky Way, or actually we're falling into Andromeda because it's the big galaxy, we're the small one, and yet the universe is expanding. And the thing is that at the local levels, at the smaller levels, the gravitational attraction between the Milky Way and Andromeda is stronger than the gravity, than this expansive force that's pushing out. So the bottom line is that gravity really has nothing to do with it. It is fighting against, at a local level, the expansion of objects being pulled apart by the expansion of the universe. But in general, gravity and that expansion have nothing to do with each other. So that is an answer to that. Whoa, I like this one. Um, let's see. All right. Fred Edison, what would a magnetar do to a black hole other than become its lunch? All right. Fred Edison, what would a magnetar do to a black hole other than become its lunch? Well, so a magnetar is is really a kind of neutron star, and you get a neutron star when a star that's much more massive than a black hole would explodes as a supernova. And again, we've done lots of episodes on that, but essentially, you've got a star that's much more massive than the sun. It's got all of these, the core, it's fusing hydrogen into helium, and then when that hydrogen runs out, it turns into helium, and then when the helium runs out, it turns into whatever is the, further up the chain, it fuses oxygen, and it fuses neon and silicon, etc., all the way up to iron. And this whole process of fusion is exothermic. It releases energy, but when you get to iron, the process is endothermic. It requires energy to put in to make it, and so the star shuts down, and all the outer layers collapse in on itself, and in a moment you get this compressed object at the heart, and this incredible explosion. And the idea is then, if the star is about 8 times the mass of the sun, you get a neutron star, and if the star is much more massive than that, then you get a black hole. A neutron star, when it's first born, right, it's rotating very rapidly, and we call this a pulsar. And then as the neutron star slows down, it becomes, various flavors of neutron stars, and one of these is called a magnetar. And astronomers aren't entirely sure what happens, like what is the cause of these magnetars, but they are the most magnetic objects in the universe. It's kind of mind bending how powerful the magnetism is with these magnetars, and a magnetar really is a version of a black hole. It's just that a black hole had more mass. The star that died had more mass, or a supermassive black hole. But they're really brothers, right? It's just the size of the object. But if you put those two together, the black hole eats the neutron star, the black hole eats the magnetar, and you're done, right? Now, it might take a second for it to consume it, and it might sort of spray out gamma radiation as it's consuming it, but the magnetism of the magnetar has nothing to withstand the power of a black hole. Nothing can. Nothing. There is no way to destroy or kill a black hole. You can't burn it, you can't stab it, you can't shoot it, you can't hit it with antimatter, you can't. The only thing that you can do to get rid of a black hole is to just wait for it to hibernate. All right, let me go back to some of the questions here. That's an interesting question. Let's do this. Sort of a little in the weeds. CUXOB2, where does the energy of the photons go? All right, hold on. All right, I pulled this image from DARPA. It's cool. Somebody doing like spinning sparklers, and you get this cool light trails. I like it. But right. So the expansion of the universe has been going on for 13.8 billion years, and what that's done is that's caused redshift, and we can see the further we look out into the universe, the faster things are going away from us in all directions. In fact, the faster everything is going away from everything in all directions, and that tells us, right? We can measure the amount of redshift, and that tells us what the sort of rate of expansion has been. And so you're asking, like, where does the energy of those photons go, right? Every photon has a certain amount of energy, which is sort of this whole idea of, you know, a quanta of energy. And you've got this wavelength, right? And over time, that wavelength stretches out. And so all of the energy is still there in the photon. It's just that it's been stretched out over a longer duration, right? Over a longer wavelength. But all of that energy is still there. And this is sort of part of this idea that all of the energy and matter, the mass energy that was present in the universe moments after the Big Bang, is still here and will still be here far out into infinity. It's just that the density of that is lesser. And so if I take a rubber band and I stretch it, it still has as much rubber band material in it. It's just that the rubber band has been stretched out. So I hope that makes sense. Sort of the time. Again, you got to give me feedback. I'm like, you know, just making new stuff up here. I've got a couple of questions here asking me some stuff that you don't have to ask your question a bunch of times. Like it could be, like, for example, some people are asking me questions about, and I'll turn that off here, about thorium reactors. I haven't done the research into thorium reactors to be able to speak about it intelligently. We did an episode on fusion, and everybody wanted to know my thoughts on thorium reactors, and I have no thoughts on thorium reactors, only because I don't. Molten salt reactors. Yeah, I don't know. Please stop asking me. I'll look it up. I'll do an episode on it, all right? Ooh, that's a good question. Okay, let's do this one because I like it. All right. Oni Chan Man wants to know about an interstellar internet using wormholes. Did I spell that right? Okay. I love this. All right, this is awesome. Great question. I'm going to interpret the question how I think you're asking it. And so this is the idea, like, one of the big problems with communicating over vast periods of time is that all communications need to go at the speed of light. And we know that if we want to communicate with folks on Mars, it takes 20 minutes to 45 minutes. If you want to communicate with a probe that's going to Pluto, it's going to take you 8 hours. And eventually, if we're trying to communicate with the folks over on Alpha Centauri, it's going to take us 4.25 years for a message to go from us to them. So is there some method that we could use that would allow us to communicate more quickly than that? And my sort of feeling on that, or the way the science looks, is that the answer is no. And people have thought, well, like, whoa, could we maybe use sort of this spooky action at a distance, quantum entanglement? And the problem with quantum entanglement is that you can sort of have these two particles and they communicate instantaneously, but to understand, for both people to sort of agree on what happened, you still have to communicate at the speed of light. But could you use wormholes as a way to communicate? And theoretically, and this is why I'm saying this, the answer is yes. And so here's how it would work, right? Is that you would create a wormhole. And once again, now, already creating a wormhole is beyond the possibility of our physics. But let's say you could, right? Then you would, create these two parts of the wormhole, and then you would leave one place in one location, and then you would move the other place far away. And you could theoretically travel through this wormhole. Now, one of the problems with sort of the physics of wormholes is it appears mathematically the second you try to put anything through the wormhole, it will collapse the wormhole. But what about information? What about just photons? Could you send photons through the wormhole? And could you have a way that you could have a galactic communication system that communicate this way? It's a great idea. We don't know if wormholes are even possible, and if they are possible, we don't know what we could use to put through them, and if we do, we don't even know if we could move one end of the wormhole. I mean, obviously the more interesting idea is this idea of instantaneous travel through a wormhole, or even better, time travel through a wormhole. So you could imagine that you could take one end of the wormhole and then move it faster and faster, so that you go at sort of relativistic speeds. And so the two ends of the wormhole have experienced different amounts of time. And so you could actually travel through one end of the wormhole and come out the other side, and you could move back in time or move forward in time, or we could communicate. And so you could even imagine, right, like people being able to communicate at time differences. Anyway, it's a mind-bending idea, and so I really like it. All right, let's do this one next. Tom Robin is asking, how fast could humans theoretically go in a spaceship safely relative to the speed of light? When you see me like looking disappointed, I'm like, I don't see a picture that's really good for this question. But I will go ahead and ask. I'll use this one from some show. I don't know what it's about. I think it's The Expanse, maybe. Anyway, how many they made the Kessel Run in how many parsecs? Anyway, so the question comes from Tom Robin. How fast could humans theoretically go in a spaceship safely relative to the speed of light? And this is a big, big, big problem for moving at having that Star Trek future that we've always hoped for. That if you're not gonna use warp travel, you're gonna use some kind of method of actually moving through the universe, which is the only way that we know how to do this. You would need to go. You'd need to go. A significant portion of the speed of light to be able to make these trips in a reasonable amount of time, right? To go, say, from here to Alpha Centauri, 4.25 light years away, you'd want to go 10% of the speed of light, so it would only take you 42 years to get to the closest star, which would still suck, right? Would you be willing to sit in a spaceship for 42 years to get to just the nearest star? Like, we don't even know if it's very good. So that would be, that is the problem. And so you really want to go faster, right? You want to go 10%, 20%, 30%, 99% of the speed of light to really kind of bring down the travel times. In fact, the really exciting part about this is, thanks to time dilation, the faster that you go, the less time you experience on these long duration flights. So we did an episode called How Far Can You Travel? And if you go, say 99.99999% the speed of light, because of time dilation, and if you're constantly accelerating, you might experience, say, 40 years of life, but you've gone 14 billion light years away from the Earth. And the rest of the universe has experienced 14 billion light years. I mean, you could absolutely get to the heart of the Milky Way. You could get to Andromeda. You could get to other, the farthest corners of the universe, because that's how time dilation works. But the problem, of course, is the speed. And so we don't know how you could move that quickly at all, right? We don't know what kinds of engine systems would even be possible to be able to get you going that fast. Could we use fusion drives? Could we use antimatter drives? Could we use light sails? I mean, light sails is the only technology right now that we have that is even theoretically possible to get you that kind of speed, because light can move at the speed of light, and photons have momentum. So you could fire a laser at a light sail, the photons would bounce off of the light sail, and the light sail would accelerate thanks to that light. And so theoretically, you could push a spacecraft to the speed of light with light. But the faster that you go, the problem is that you are plowing through the interstellar medium at the speed of light, or at, say, 10% of the speed of light. Now, we know that around the sun there is this protective, well, not necessarily protective bubble, there is this bubble where the light from the sun, the solar wind from the sun, reaches the interstellar medium, and the two kind of smash together, and it creates this bubble, this heliosphere around the sun. So that interstellar medium is absolutely out there. Space is not empty. Space is filled with particles. It's filled with radioactive particles from other stars. And then cosmic rays and things that have come from supernova explosions and supermassive black holes. It's a dangerous place out there. And so if you're going to be trying to moving at 10% of the speed of light, and you're gonna be smacking into these tiny little pieces of dust, they are going to be hitting your spacecraft with an enormous amount of force. And it's going to be like sandpaper times 1,000. It's just going to be wearing and grinding down your spaceship. So that is really the biggest problem, I think, as we learn to make our spaceship go faster and faster and faster. We're going to run up against this sandpaper of space that's going to cause all kinds of problems. What is the fastest speed? We don't know. We're going to have to find out. We don't know what the density of the interstellar medium is. We don't know how many of these things are going to be smashing into us. This is still an unsolved question. There's going to be some attempts eventually from Breakthrough Starshot where they're going to try and send microscopic sized little solar sails, microscopic probes on a solar sail out to some other world, and we're going to have to see how well that works. I'm excited for us to try, and I will not be on a spacecraft until we know that it's safe. And Oni Chan Man is saying we just need some Star Trek level of ship shielding. Yeah, absolutely. We need to surround the spacecraft in some kind of magnetic field. But then what if, are grains of sand magnetic, right? How do you make a force shield? So this is a really complicated problem. And it could very well be that we will, except for 50 meters of lead shielding at the front of your spacecraft, we don't know of any way to prevent it. You just kind of got to take the hits as you make the journey. And it might be like that high speed travel between worlds is impossible, right? Let that just sit in your soul for a little while there, and just know that we may never be able to travel to other star systems in our lifetimes, that only the patience of our robotic overlords will be able to do this. Let's do this one. Go Naidu wants to know about not able to find life beyond Earth. Oop, you don't want to have to hear this. Gotta remember all the things I have to do. All right. So this is a great question. It comes from Go Naidu, which is like, why have we not been able to find life beyond Earth until now? Do you feel that Europa might have some kind of microscopic organisms that live off of hydrogen? That is a great question. We have, but partly we've only really been looking for life beyond Earth for the last few decades, really. We've only just begun to look. And we learned back in the 1970s with the Viking missions that we weren't ready to definitively answer whether or not there's life on other worlds, right? We know that there are other explanations for what was discovered in the Mars Viking mission, and so NASA kind of really went back to the basics and said, well, we've got to do this right. The question of whether there's life on other planets is so important that we've got to make sure that the evidence that we find is overwhelming. And so they went back to the drawing board and came up with this very kind of more deliberate and slow attempt to try and answer this answer. And so they've been searching for evidence of water on Mars, which they found. They've been searching for evidence of that water was on Mars for a long period of time. And the next rover that's going to go, the Mars 2020 rover, I don't know if it's got a new name yet, it's going to be searching for sort of evidence of past life. So we are getting to that point. And then, as you said, over on Europa, they're finding evidence that food for bacteria is emanating out of the ice on Enceladus and out into space. And so we know that those exact conditions on Earth have mountains of life, down at the bottom of the oceans, these black smokers. And so the first part of it is that it's obvious that life isn't everywhere. Right, we would see trees on Mars, and we would see crazy life forms, and we would see balloon organisms floating in the cloud tops of Jupiter, and the Plutonian ice monsters would have waved as we went by. So it's not large life like what we have on Earth is clearly not common in the solar system. We don't know if it's common in the universe. We still haven't gotten that far to check. But the reality is that we are narrowing down what the possible parameters are for life on other worlds here in the solar system and across the universe. Our ability to detect life is getting better and better and better. And over the next, we keep talking about this in the various shows, that in the next decade, you're going to have the James Webb Space Telescope and other amazing both ground and space-based telescopes, which are going to allow us to directly analyze the atmospheres of other planets orbiting other stars. And you're going to be able to say, oh, there's life on that planet right there. Now, we can't see what kind of life it is, but we know that it's there, and we know there's life over there. We haven't been able to detect life over there. So once that detection gets made, that is going to change. I think it's going to change everything, right? We're going to see this. We're going to know and be able to look at all the worlds that are surrounding us and go, there's life there, there's life there. Oh, there's an pre-industrial civilization over there because they've filled their atmosphere with coal fires. And then, and there's an industrial civilization over there because, and they just had a nuclear war because we'll be able to detect this in the atmosphere of those planets. So stay tuned. I think we are watching this in the unfolding of our discoveries of the universe. We are watching this unfold in real time, and you are being a part of it. You come to this place with a sort of, all of the settled science about plate tectonics and how volcanoes work and why the sky is blue and the discovery of all these other things. And then you have all this other stuff that astronomers and scientists are figuring out, and you're here to watch it, and you're going to watch them stumble, and you're going to watch them make new discoveries and start to piece this together into a larger tapestry. And I think that's really exciting. And I love that a lot of these things, we just don't know the answers to them. And sort of on that, so Peanut Butter is saying, is atmospheric spectroscopy able to rule out other possibilities? Yeah, there are certain conditions, Mr. Peanut Butter, that that could only be created by some kind of life. If we saw, I think some of them, and astronomers have actually put together some of this criteria. So there are like certain amounts of ozone in the atmosphere, that there would need to be some organic process that is providing this. So that is, I think, where we are, where we're at is within the next decade, instruments like James Webb will come online, and we will get a chance to answer this question, hopefully definitively, right? I hope we will see the signature of life on another planet orbiting another star. All right. All right. Let's just do this. Sure. All right. AG wants to know about math. So let's do that one, because I'm actually dealing this with my son right now. Hold on. I should be able to find a bigger picture. Apologies. All right. I was going to try and find some gravitational formula here. I wish those stayed in the same place. Anyway, I'll figure it out. So we get this question a lot. We get this question a lot on Astronomy Cast, and a lot of people will say, I'm fascinated by space and astronomy, but I'm really bad at math. So I can't be an astronomer, or I can't be an engineer, or I can't be a space scientist, or Elon Musk will never hire me to make reusable rockets. And I want to challenge your assumption that you're bad at math. Almost nobody is good at math, right? Math is kind of like learning a language, and you don't just intuit a language, right? If when you learn French or you learn Spanish or some other language, you don't just kind of go like, I'm good at languages, I'm bad at like everybody is bad at other languages, and we have to pick them up bit by bit by bit, and we practice them, and they extend on each other and move from there. And so I think that, if you are interested in moving in, working on some field that has anything to do with math, and most of the fields that are really interesting do, right? All the sciences, if you want to work with computers, there's a ton of math in there, and so on. And so I think the first thing you need to do, if you're like considering this, is like, if you are listening to this and you're like, I'm really bad at math, so therefore I can't be a whatever, you're so wrong, right? Nobody's great at math. It's just that some people are willing to put themselves through the time it takes to learn each piece of the puzzle and build that extension of the mathematics. A couple people are mentioning this in the comments, like the using Khan Academy. I highly recommend Khan Academy. I battle with my children on Khan Academy on who can have the more points, and so whenever they get better, I'm not going to let them beat me, so I get more points on Khan Academy and keep my math going. But it's practice. And then once you become a professional astronomer, you're going to be working with the same math again and again and again and again, and you'll get really good, really well practiced at running those calculations. So I think that what math you're going to be taking, you're going to be, if you're going to go into astronomy, you're going to go into physics, you're going to go into engineering, they're going to recommend the math you should be taking. If you want to prepare yourself, then go to Khan Academy and just keep doing math and moving yourself up to, say, pre-calculus, and then you'll decide whether you want to keep going with that. But when people tell me they're not bad at math, not good at math, it drives me crazy. So that's my feeling. And so Oni Chan Man is saying, yeah, I'm studying computer science. It's kind of creative in a really fun way, and I totally agree. My background is in computer science, and see, there you go, Emery Cozy, you're not bad at math. You just have not practiced your math long enough. I don't want to hear a single one of you say that you're bad at math. Don't you say it. Okay. All right, so let's go with a last question from Eunice Sofree. What if a space probe stops in space? That's clearly going to drive me crazy how it zips around each time. All right. So, what if a space probe stops in space? How would it stop? Like, are you saying, like, so, could you please provide some more information here? But like you've got a spacecraft that's traveling along and it crashes into something, it litho breaks into another world, then it's destroyed, right? But space is all about orbits, and I highly recommend you, if you haven't already, play. Okay, I've had very little practice with math. You happy? Yes, that makes me happy. That's perfect. Sorry. So I highly recommend you play Kerbal Space Program because it will totally change your understanding of how spacecraft move through space, how the different orbits work, how you can raise and lower the orbit, how like for example, we always talk about this idea of what is a suborbital trajectory, what is an orbital trajectory, what is an insertion orbit, and so when you ask like how can a space probe stop, you really kind of have to see this in the context that everything is relative, right? Everything like compared to what the 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 spacecraft could be going around the Earth, but the Earth is going around the Sun, and the Sun is going around the Milky Way, and the Milky Way is part of the local group, and that's part of the Virgo supercluster and the Laniakea supercluster, and it's part of the Bootes wall, and you know what I mean? Like there is these great big structures that that the spacecraft is always moving in compared to everything else. So I think that if you had more specifics, that would be helpful. But yeah, I think I highly recommend, if you haven't already, play Kerbal Space Program, and it will give you just a really deep understanding of exactly how spaceflight works and how you can move from place to place. All right, well, it's the end of the hour. Man, that went by really fast. That was a lot of fun. Again, give me feedback, please. Do you like this format? I don't know. Would you prefer if I just had a guest and we'd be? I'm trying. Like I said, I put those questions up, and I'm trying to sort of take some time to give people who are watching this some context for what's going on in the show, as opposed to just being me going blah 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 blah. But never know. That's fine. So please let me know what you think. And what's coming up next? We've got a new episode coming out tomorrow, and it's all about the Parker Solar Probe. So that was the recently renamed spacecraft. We got a QA on Wednesday, and then on Thursday we're going to be talking about seeing the universe in gravitational waves, and sort of what's next in gravitational waves. What can we see? How far back can we go? What is the limits of gravitational waves? And it's pretty exciting because the limits are we'll be able to see beyond the cosmic microwave background radiation right to the Big Bang, or right till moments after the Big Bang. So that's going to be pretty exciting. So, and I wanted, Sergio Botero is in the chat right now, so I just want to point you at Sergio. If you haven't already, check out his stuff. Sergio was one of the artists that did a bunch of graphics for the collaboration that I did with Isaac Arthur, and he did the cool sort of scooping ships that are moving through the gas planets, and he did the mining operation ship, the mining rovers, like these gigantic tank things that were moving around on the moon and pulling up helium. It was super fun. So big thanks to Sergio for doing that. And seriously, man, I cannot wait to work with you again. I had so much fun, and you brought so much sort of imagination to what we were doing. It was really exciting. So please, by all means, let's do something else. All right. Well, thank you everyone for joining me today. Again, give me your comments, feedback, let me know what you think, and maybe I'll do this again next week. See you later.